Yeah, welcome back to the CS4423 networks. My name is Götz Pfeiffer and this video is about lecture 2, graphs and the networks package. A graph can serve as a mathematical model of a network. It simplifies the information, the real-world information usually attached to a network, and it makes the network structure applicable to mathematical investigations, algorithmic methods, and so on. We'll use the networks package here to work with graphs and networks. And in this lecture, I want to give a brief introduction to graph theory, introduce the language of graphs that we're going to use, along with some of the basic functionality that's provided by the networks package. So to begin with, we load the networks package, we import it into the current session using Python's import command, and then we call it nx for short. So then we can use the nx prefix to call on functionality provided by the package. There it is. So let's start with an example. Here is a map of the internet back in December 1970. At the time it was a rather small network connecting a few computers on the east coast of the US to a few computers on the west coast, and them amongst each other. 13 computers in total, connected in the way indicated here. And as far as the connectivity is concerned, the bare network structure can be expressed in a much more compact way. For example, in the following file, which lists the adjacencies between the nodes in the adjacency format indicated here by the .adj file extension, where now each line in this file starts off with a node name and afterwards lists other nodes that this node is connected to. So UCSB is connected to SRI and UCLA, as in the map here, UCSB connected to SRI and UCLA. Then SRI in turn is connected to UCLA and Stanford and Utah. SRI connected to UCLA, Stanford and Utah here. The fact that SRI is connected to UCSB has already been mentioned in the first line here, so it doesn't need to be repeated again. And so on. So that's how to read this file, listing connections and node names at the same time. The networks package is aware of this format. There's a function read edge list, which can be applied to this file, and which then uses this information, reads it as nodes and edges between them, and turns it into a graph object. I call this object H here, and then I use the package to draw the graph with these two options. I ask it to draw the node labels as well, and to use yellow as the node color. These options I've packaged into an options dictionary, which then is passed to the drawing function call using this double star operation, which unpacks the dictionary into its individual key value pairs. That's what the function actually expects here, individual options with values. That's I'll be using this throughout for drawing graphs. That's why I've packed it away here into a single dictionary. Anyway, if we send this away, we get the following drawing of the network. which has these labeled nodes connected as they were in the map, but it doesn't have the distracting details of the geography with it anymore. It can space these nodes in equal distances where possible, and reduce the number of crossings between these edges. So you get a much more compact, much more easy to read graphical representation of this network. And that's how the language of graphs, simple graphs in particular, enters the networks theory. So to remind you, or to give you a definition if you haven't seen this before, mathematically a graph G is a pair of two sets X and E, where the X set is a finite set of objects, which are called nodes or vertices in this context, and the E set is a set of two-element subsets of nodes of the node set, called links or edges. I use this binomial notation x choose 2 to indicate the set of two-element subsets, the possible edges of this X set of nodes. Now that's the definition of a graph. A simple graph, simple in parentheses, because if I say graph I mean a simple graph. And simple graph in contrast to other things that other properties a graph might have means that the edges go both ways. They have no directions. They are subsets with two elements. An edge is either present or it isn't. There's no multiplicity. There aren't multiple edges in such a graph. And an edge joins two distinct nodes. And there are no loops. There are no self loops attached to vertices in a simple graph. That's a simple graph, my favorite graph object, because it's simple. So a graph being a pair of two things, there's two natural measurements that one might take on a graph. How many objects are in the X set, how many objects are in the E set. Usually the letter N is used to denote the number of vertices, the size of the X set, and this is called the order of the graph. And the letter M is used to denote the number of edges. That's the size of the E set, which is called the size of the graph. So I've set this x choose 2, this binomial notation is used to denote the set of all two-element subsets of the X set. It's motivated by the fact that there are actually n choose 2 elements in there. N choose 2, that's half of n times n minus 1. Now the number of possible edges on an n element set is n choose 2. The number of possible edges on a graph of a set X of objects is size of X choose 2. And this then obviously provides an upper bound for the number m of actual edges that are present in a given graph. The number m is always bounded by n choose 2 if there's n vertices to be connected. Here's an example. The example we saw yesterday. The X set is the set of letters A, B, C, D, 4 of them, and as edge set, here we have 4 edges, A, B, B, C, B, D, and C, D, where I've used the word A, B as a shorthand for the two-element set AB. That's it for now, the brief introduction into graph theory. What do we want to remember? We want to remember that a graph is a pair consisting of a vertex set and an edge set. N is the letter to denote the number of vertices, called the order of the graph, and M is the letter that denotes the number of edges, and it's called the size of the graph. The relationship between the two is that M is bounded by N choose 2. Now, in the networks package, we can construct such a graph with the graph constructor, and the graph constructor takes the edge sets and the vertex sets or edge sets in a variety of formats. For example, we can use, in much the same spirit as I've used 2-letter abbreviations here for 2-element sets, we can use 2-letter strings for a description of the edges, and implicitly then this describes the nodes that are used, the nodes that this graph lives on at the same time. So this graph up here we can construct as the graph on the edge list A, B, B, C, B, D, C, D. Pass this to the graph constructor in the networks package. This gives, as a result, an object, a Python object G, that represents the graph and has lots of attributes describing the graph. For example, it has nodes and edges, and these can be accessed as g.nodes. That gives a nodes view object. Do we want to know this? I guess not. So for practical purposes, we turn this into a list, and there's a list of nodes A, B, C, D. Similar for the edges. Internally, this is an edge view object. If we turn this into a list, we get a list of pairs of nodes A, B, B, C, B, D, just as we provided it as input for the graph construction. Well, it might be, in the long run, it might be useful to have a means of looping over all the nodes in a graph. And this can be done with a standard Python for loop. A loop over the graph for node in G will simply loop over the nodes of the graph. We can, like this, loop over G. For node in G, print the node name A, B, C, D. And we can ask the G object for its number of nodes, which, as I said earlier, is the order in graph theoretic terms. There's 4 of them. We can ask for its number of edges. That's the size of the graph, and that's 4 again in this example. And we can ask the package to draw a graphical representation of the graph using the same options dictionary as before. We get a nice drawing which has the 4 labeled nodes in yellow here, connected by edges as requested. Now that's a typical way to represent graphs as diagrams. The nodes are little circles, and edges are represented by straight lines connecting those circles, connecting the nodes. This G object can be modified, for example, by adding nodes one at a time. We can use the add node method to add a node called 1 to the graph, and then asking it for its list of nodes. In addition to A, B, C, D, we now have 1 as an extra node there. Nodes can be added from a list. Many nodes at the same time. 2, 3, 5 added to the list of nodes. Gives additional nodes 2, 3, 5 in the list. Or we can copy nodes from another graph. Let's take the internet graph H from above and copy the nodes from this graph to our G graph, and then we get a list of nodes which in addition to the ones we already had now has all the nodes of the small internet graph from before. This is now a graph which has order 21, 21 nodes in total, and still has size 4. We haven't done anything to the edges, still the 4 original edges. But as you might imagine, edges can be added as well, one by one. Now, here we add an edge 1, 2. So asking G for its list of edges in addition to the ones we already had. Now we have an edge between vertices 1 and 2. Note how this edge is added as an edge between two individual arguments, 1, 2. If we have the edge, as in the next cell here, given as an explicit pair of 2 and 3, before we pass it into the add edge method, we need to separate the 2 from the 3. We need to get rid of the outer parenthesis here. Similar to the double star dictionary unpacking, we can use the star list unpacking here, which gets rid of the outer parenthesis and passes the 2 and 3 individual to the add edge constructor. If we pass this edge object as star edge into the method, then it adds this as an additional edge. And similar to before, we can add edges from a list, and we can add edges from another graph. We can add all the edges from h.edges, and then we get a long list of edges. And now if we draw the graph, we have a larger graph which consists of the original graph that we constructed, a small graph on the nodes 1, 2, 3, 5, and there is a copy of the internet graph. All in one graph, different components in one graph. This graph now has 21 vertices and 26 edges in total. Going the other way, there are commands for removing nodes or edges. We can remove the edge between 3 and 5, again passing 3 and 5 individually as node names. And then asking the graph for its order and size. We've seen that the size has gone down from 26 by 1 to 25. We've removed an edge. We can remove all the edges from the H graph at once. And then if we draw the graph, all the nodes in the H graph are disconnected, floating around here, singleton vertices. So if we no longer want them, we can remove them using the remove nodes from command. And if we then draw the graph, all that's left is these two graphs on A, B, C, D and 1, 2, 3, 5. And finally, if we remove nodes from a graph, this as a side effect will silently delete all the edges that the node was involved in. So removing 1, 2, 3, 5 as nodes from the graph will actually remove this entire component, nodes and the edges between them. and leave us with the original graph on ABCD. That's one. That's adding and removing nodes on a graph object. Within the graph, each node has neighbors. That's a technical term for the nodes it is directly connected to by an edge. We can get a list of neighbors by asking the graph for the neighbors of the B node, for example. And that gives us ACD, since B is connected to all three of them. The same information is obtained by just adding by just accessing the component B of the G object, which gives this gives an atlas view object, which we don't really want. So let's turn this into a list. So the list of the B component of G is the list of the neighbors of B. Well, that might come in handy later when we want to investigate neighbors, and I don't know. The number of neighbors of a node in a graph is called the degree of the node. We can ask the graph G for the degree of its B node, and we can ask the graph for all the degrees, which is a degree view object. If we turn this into a list, we get a list of pairs of node names together with their degrees. The A node has one neighbor, B, as we already know, has three neighbors, C has two neighbors, and so has D. Well, that's the basic functionality of graphs and graph objects in the networks package. Let's use this to construct some standard examples, starting with maybe a complete graph. A complete graph on a vertex set X is a graph which has all possible edges, which has X choose 2 as its edge set. So for example, we could try and use as our node set the range of 5, which in Python, as you know, is the list of numbers from 0 up to, but not including 5. It's the 5 nodes, 0, 1, 2, 3, 4. And to list all these 2-element subsets, one can use list comprehension to make all pairs of X and Y, all pairs of nodes X and Y, with the condition that X is smaller than Y. So to make it a set, say, to not overcount pairs. And we get the list of all, how many 5 choose 2 is 10. 10 pairs of 10 subsets, 2-element subsets of this set of nodes. Well, that's, I guess, somewhat straightforward, but maybe on the long run it's more convenient and possibly more efficient to use the Python itertools package to make such 2-element subsets. The itertools package has a function combinations, which does exactly that. Combinations applied to nodes with parameter 2 computes all the 2-element subsets of nodes. Here as a Python object, as an iterator, I suppose. Okay, let's turn this into a list. And there we get the same list of 10 nodes, 10 edges between those 5 nodes. And this list we can then use and pass it into the graph constructor to construct the complete graph K5 on 5 vertices. And if we draw it, if we draw this, we get a complete graph on 5 vertices. And the 5 vertices connected in all possible ways. That's a nice combination of Python commands and the networks functionality, and maybe with a bit more Python skills we can turn this entire procedure into a Python function that takes a list of nodes here as input and then produces as output the complete graph on this set of nodes. By using the commands we've used before, we can define this as a function, call it complete graph with argument nodes, and then we can use this function to draw a complete graph on 3 nodes, 4 nodes, 5 nodes, 6 nodes, or on the vertex set A, B, C, D. In fact, this is such a standard example. The networks package has its own implementation of this of the complete graph. It's called complete graph, same as ours. To access it, we use the nx.prefix here, and we can apply it to the node set consisting of the letters of the word networks, and it constructs a complete graph on this set just as before. I find this useful to before using the functionality provided by the package, to think, how would you do this by hand? How would you do this as a Python program? See how it works, see what's necessary, what are the challenges, and then when you use the function provided by the package, you have some understanding how this works on the inside, some understanding that helps to estimate how much time it will take or whatever. So similarly, I'm going to treat this nice example of the Peterson graph. Peterson graph, by definition, it is an interesting graph which serves as counterexample to many guesses on properties of graphs that you might have. It's a graph on 10 vertices with 15 edges, so it's relatively big by our standards now. And that means I wouldn't want to type this in by hand. So I'll use a more abstract definition of this graph as the complement of the line graph of the complete graph K5 that we just constructed. That is, this is a graph which has as its vertex set X the edge set of the K5 graph, and any two such vertices, which are edges in the K5 graph, which are 2-element subsets of the 5-element set, are connected in the Peterson graph if, when regarded as sets, their intersection is empty. That's a mathematical short description of this relatively large graph, and this is how I would construct it. Starting with the K5 graph that we've seen before, and we extract the edges of the K5 graph, call it lines here, and then this lines list serves as the vertex set for the Peterson graph. So the possible edges of this set then are pairs of these lines, and pairs of these 2-element sets, and that's one level of complexity added. And there's many of them. We want to, in order to satisfy the definition, we need to filter out those pairs of edges of the K5 graph which have an empty intersection, which don't use a common endpoint. So this is a bit of set calculations. Sets are represented in Python. I don't know whether you've seen them. They're basic objects in Python, and they can be obtained with the set constructor or the set converter. And set intersection is represented by the ampersand operator. So I can form the intersection of the two lines that make up an edge in this set of possible edges by taking its zeroth entry and the second entry, turn them both into sets, and then form the intersection. Then I can use this intersection as in a Boolean context, with the Boolean not here, as a condition, using the fact that the empty set in a Boolean context serves as a Boolean false, and a non-empty set would serve as a true. So set emptiness can be used in a Boolean context to make decisions, to distinguish cases. So here, long story short, I construct an edge set as those edges E in the list of all possible edges there between the lines of the K5 graph, which have a non-empty intersection, which have an empty intersection. And then I get 15 edges as required. I can define the graph on these edges, and this illustrates the flexibility of the package of the graph constructor. The vertices in here don't have to be letters or numbers. They can be anything, in particular lines from the K5 graph. And then I get the Peterson graph, or a drawing of the Peterson graph in this form, where, as you see, the vertices are what used to be edges in the K5 graph, pairs of numbers between 0 and 4. And since this worked well, we can again try and wrap this up into a Python function. I'll call it Peterson graph, and then we can construct a Peterson graph from this function whenever we feel like it. And draw it. So that's that. There's a bit of documentation for the Python elements that I've used, networks elements that I've used, and the iterator tools, and a couple of exercises for you to work through in your own time, if you wish.